Okay. Okay, vamos a continuar. We go on with a session. Now we are very happy to have Alain Aspect here. He is a famous guy who tested the Bell test, the Bell inequality testing the Einstein-Podolsky-Rosen experiment, and he is currently professor at the Institut d'Optique et École Polytechnique. He received numerous awards and prizes. He has 6 honorary doctoral degrees of freedom and is officier de la Légion d'honneur and member of the French Academy of Science and of Technology. So it's it's an honor to have him here, and we are very curious to hear about your research.
Thank you very much for this introduction. It's always a great pleasure to be here, and I've been here several times, and I'm afraid that I've already given this talk several times, so I have prepared something on what we do at the moment in my group. That is to say, actually, we repeat the milestones of quantum optics, not with photons, but with atoms, okay? So the last results are the Hongwu and Mandel experiment. We heard about photons, but we have done it with ultra-cold atoms. We have also a program on Anderson localization. We heard of Anderson localization. We do it with atom also. But van der Leeuw insisted that in this context of the year of light, with students who were not even born when I came here for the first time, okay, I should present what I would call my standard talk on Bell's inequality. So when van der Leeuw asks something, I have to do it, so I will do it. Okay? But I apologize for the people who have already heard it. If they sleep or do their mail or things like that, I will not object. But young people, please listen to me. It's an interesting subject. Okay, so what do I have here? This is a book of which I am the author, and all the calculations necessary to understand what I am doing here, I explain in this book. Actually, the subject which is here, you find it as a complement in this book. And in addition, if you buy this book, or if you insist that the library should buy this book, I get some royalty, maybe 3 or 4 euro or something like that, a royalty, okay? So it's good for me. Now, if you don't want to pay, you can also go on the web, or you can go to my homepage, and you will find basically a text corresponding to that talk. Okay. So, I will first talk about quantum information and try to give my point of view of how quantum information emerged. Then this will be the core of my talk from the Einstein-Bohr debate long ago, 80 years ago, to Bell's inequality test and the emergence of the notion of entanglement. And I will advocate that with the more and more use of entanglement, we are living a real new quantum revolution. And you see who are the heroes of that story: Albert Einstein, Niels Bohr, Schrödinger, John Bell, and Richard Feynman. Okay, if you type quantum information on Google, well, I did it 2 years ago, okay, I should do it again, but at that time it was 55 million answers, okay? And the first answer coming, I have them here. You have an organization, quantum information, a virtual journal of quantum information. The New York Times speaks of quantum information, which means that it is certainly a very important subject, okay? Because we know that physics is best done on the New York Times than anywhere else. There is at Caltech an Institute for Quantum Information. There is an Institute for Quantum Information in MIT, in Cambridge, UK. So clearly, quantum information is a big deal. And so we can ask the question, how did it emerge? And I will give you my understanding. I think that it emerged with a discussion between Einstein and Bohr, again in 1935, that is to say 80 years ago. Schrödinger put his grain of salt in the discussion. It was the same year, 1935. And then we had to wait, or they had to wait. I was not born at that time. So physicists had to wait until a paper of John Bell in 1965. So you say it's still anniversaries, okay, 65. So we are 50 years after this work of John Bell. And so what Bell really found is that, and there is really something very special in entanglement. Einstein and Schrödinger had guessed that there was something special. John Bell demonstrated that there is something special with entanglement. And then later, in 1982, Feynman had not realized until this point that entanglement was different. And in 1982, Feynman realized that entanglement is really different. But Feynman being Feynman, I encourage you to read this paper. Feynman being Feynman, as soon as he realized that entanglement is really different from what? Different from what we had before in quantum mechanics, wave-particle duality and these kind of things. When he realized that it is really different, he said, okay, let's use it for something. And he invented the notion of quantum simulation and quantum computing. Okay, so this is a story I'm going to tell you. Whoops. So let us start with the Einstein-Bohr debate. So if you don't know, you should know that the relationship between Einstein and quantum physics is really very strange. In 1905, 110 years ago, Einstein wrote what we can consider the real founding paper of quantum physics. You are going to tell me, what about Planck? Yes, of course. Planck, 1900, was the first to write the Planck constant and to write a relation like E equals h times the frequency. But what Planck did was assuming that the exchange of energy between black body radiation and matter are quantized. Assuming that the exchange is quantized was much less revolutionary than the hypothesis of Einstein in 1905. Einstein said the radiation itself is made of grain of energy. He called it least quantum. It was called photon later by an American chemist, Gilbert Lewis, in 1920 something, okay? But Einstein introduced the idea of least quantum. The radiation itself is quantized, okay? And this paper of Einstein was very badly received by the other physicists. And we know it because in 1913, Einstein was admitted in the Prussian Academy of Sciences. And we have the reports, which was written by the great physicists of that time, Planck, Ernst, several people like that. And it's very clear. They say sometimes Einstein misses the target. For instance, with this very bad paper about the photoelectric effect. It is his paper. But he has done so many good things that we propose to anyway admit him in the Academy of Sciences of Prussia. So it was very well received, but in 1915, Millikan, an excellent American experimentalist, did experiment. He says himself in his memoir that he embarked into this experiment to disprove this stupid law of Einstein, and at the end of the experiment, he had to acknowledge that Einstein was right. And when Einstein received the Nobel Prize in 1922, he received the Nobel Prize for this paper, for his paper on the photoelectric effect. Anyway, in these years, 1920, Einstein got more and more dissatisfied with the way quantum mechanics was developing around Niels Bohr and the people around Niels Bohr in Copenhagen. When I say the way it was developing, Einstein had no objection to the mathematics, to the algebra that you use for quantum mechanics. But he was not happy at all with all the interpretation behind it, and in particular with the interpretation of complementarity about, to be a little too schematic, wave-particle duality. And he came with many objections about Heisenberg relation, wave-particle duality, and complementarity. And I must say that Bohr always came with a reply which was very convincing. So all the objections of Einstein about, in a broad sense, complementarity and wave-particle duality were clearly answered and replied by Bohr. But in 1935, Einstein, with his colleagues Boris Podolsky and Nathan Rosen, came with a completely different objection to the way quantum mechanics was interpreted by the Copenhagen school. And this is a famous EPR that I will explain you, but he discovered something totally new, which is entanglement. And this objection of Einstein, in my opinion, was not refuted by Niels Bohr. I will tell you a little bit of it. And so it was there for decades until in 1964 or 65, it depends what you look exactly, Bell came with the Bell theorem and the situation changed completely. This is what I am going to explain. Okay, so let us come with the equation that Einstein, the sound is okay? Sometimes I hear a vibration. No, it's okay? So the equation that was raised by Einstein and his colleague, Podolsky and Rosen, is the following. You all know that quantum mechanics makes probabilistic prediction. It tells you if I do this, I have a 30% probability to get this result, 70% to get this result. Doesn't this tell us that in fact there is a more precise theory below it, of which quantum mechanics is just a kind of statistical theory? So this is the equation and the prejudice of Einstein. And with this EPR reasoning, Einstein and his colleagues thought that they have demonstrated that you need to introduce some underlying level, okay, called hidden variable or supplementary parameter, whatever you want. And I'm going to explain you that, and you will see that how Bell's theorem has changed the situation. So let us start. I have a, you know, this is a wonderful small object. The laser is okay, but the electric contact is a problem. As you know, in equipment, usually it's the electric contact which make trouble, and so it's not optics. So we are celebrating the year of optics. There is no problem of contact with optics, but here I have a problem with electric contact. Okay, so what is the Einstein-Podolsky-Rosen situation? I will describe it not in the initial presentation of Einstein, Podolsky, and Rosen, but in the presentation with photon, because it is with photon that experiments have been made. So let us suppose that we have a pair of photons emitted by this source. One is going to the left, one is going to the right, and to avoid any confusion, one is red, one is blue, so they are absolutely distinguishable. You can say the red is going to the left and the blue is going to the right. Now what are you going to do on this photon? You are going to measure polarization. You know what is a measure of polarization. If you have a beam of light, you put a polarizer in front of it, and if separation of polarization. If light is polarized along this direction, it will go in the, let's say, ordinary output, and if it vibrates perpendicularly, it will go on the other output. There are two outputs in the polarizer, okay? Now, if I am at an angle, I have the Malus law. There is a fraction cosine square of the intensity going here, and a fraction sine square going in the other one. Now, when I have a single photon, I don't split the single photon in parts. So what I have a probability cosine square to go in this channel, and a probability sine square to go in this channel. So here I have an apparatus which make a measurement of the polarization of this photon, and sometimes I find +1, I label it +1, it could be yes or no or whatever you want. So sometimes I find +1, sometimes I find -1. If I repeat many times the experiment, I can look at the probability to get +1 when the polarizer has the orientation A. Okay, A is a small unique vector that tells me what is the orientation. Same thing on the second photon. I measure the polarization, and I can measure the probability P plus and P minus to find the result +1 or -1 when the orientation is B. I can do something more interesting, which is looking for the joint detection probability. That is to say, I send a pair. What is the probability to get +1 here and +1 here if the orientation are A and B? I repeat the experiment many times, and I can measure this probability. It's P plus plus of AB, etc. And I can measure P plus minus, P minus plus, P minus minus. Okay, so here there is not yet anything of Einstein-Podolsky-Rosen. Einstein-Podolsky-Rosen comes, okay, now, okay. Einstein-Podolsky-Rosen comes when I am able to prepare the two photons in that state of polarization. Don't be afraid, you have studied a little bit of quantum mechanics, and even if you have not studied quantum mechanics, you can easily understand what means this state, and it is a big discovery of Einstein, Podolsky, and Rosen. Here I am describing only the polarization of the photon. I don't consider the propagation and all the other degree of freedom. I only speak of the polarization. If I create, look at the axis here, this is x-axis. If I could create a pair of photons polarized along x, I would describe it by this ket. XX means both photons are polarized like that. But there is another possibility, YY. Both photons are polarized like that. What Einstein, Podolsky, and Rosen consider, it's a linear superposition of XX and YY. Because quantum mechanics being linear, if a first state is possible and a second state is possible, the superposition of these two states is also possible. And now you have this state, which is a superposition of this and of that. And if you are optics people, be careful. This is not a state polarized like that. It's totally different. A state polarized like that would just be x prime, or x prime being the diagonal. Here, it's something else. If you try to re-express each of these vectors, x or y, in any other base, you will discover that there is no way to make it as a product of a photon with a given polarization here and a photon with a given polarization here. It's this plus that. And in a sense, this plus that is as surprising as the famous Schrödinger cat, which is both dead and alive. Try, and you will not succeed in factorizing that. Okay, with this state, what EPR do, or EPR-like reasoning, is the following. We calculate, and this is an elementary exercise, I would say, in the third year of university, so buy my book, you will see how to do the calculation, okay, or ask Vanderlei. So you do the calculation of the various outcomes of the measurement. So P plus and P minus. And surprise, P plus and P minus are equal to 1/2, whatever the orientation, which means that from the point of view of measurement of the polarization of this photon, everything happens as if this one was unpolarized. Okay? Unpolarized light gives 50% chance to find the same result, whatever the orientation. Same, of course, on the other way. So this is the result of the calculation. Now, the result of the calculation for the joint probability is much more interesting. You find here 1/2 of the square of the cosine of the angle between the two polarized, okay? A, B. So this is the angle between A, B. P plus minus equal P minus plus equal 1/2 of sin to the square. You can check that the sum of the four probability is 1, as it should be. And I claim that this shows a full correlation between what happens here and there. It's not obvious at first sight because there is a 1/2, but I tell you why there is a full correlation. Take the angle AB equals 0. So the two polarizers make measurement along the same direction, whatever this direction is, okay? Make the measurement along the same direction. Now P plus equals P minus minus equal 1/2. But remember that the single probability is 1/2. So, if I have a photon arriving here, the probability to get +1 is 1/2. But the probability to get +1 and +1 is also 1/2, which means that the conditional probability is 100%. So in other words, what happened? This photon arrives here. You have 50% chance to find +1, 50% chance to find -1. But if you find +1 here, then for sure you find +1 here. And if you find -1, it is certain that you find -1 on the other side. Full correlation. If you are not yet fully convinced, P plus minus equals 0. So if you find plus here, you are sure not to find -1 there. So you have a random, you have a coin, okay, head. Look, so you throw a coin here and you find a random result. You have a random result here, but if you get plus here, it's plus here. If you get minus, minus. So you have strongly correlated outcomes. Now, what can we do with that? We have, first, a little technical point. In the general case, when the angle is not 0, we have to define the correlation coefficient. We define it in the classical way. That is to say, when you have two random variables, there is a simple way of defining the correlation. It's to compare the average of the product and the product of the average. If they are not correlated, the average of the product is equal to the product of the average. So from this classical definition, we define the coefficient of correlation, and in this definition, which is classical, we inject the result of the quantum calculation. And so we get the correlation, because when I look at the result, they are classical. Okay, I have an apparatus, I have a click, all this is classical. It looks like a classical random variable. So I use this classical definition, but now I calculate the correlation coefficient with the prediction of quantum mechanics, and the result is written here. The correlation coefficient predicted if quantum mechanics tells me the right result is cosine of 2 times the angle. If you make the angle equal 0, you find the correlation coefficient of 1, as I told you already. If the angle is 90 degrees, you find -1. -1 means total correlation again, because if you have +1 here, then -1 for a cross polarizer corresponds to this again. Okay, so everything works, and in between it has a value which is what it is. Okay. Now, when a calculation predicts something, some people are just happy with the prediction, and other people, and I belong to that category, want to understand. What means understanding? It means making a kind of image, okay, of what happens. And so I would like to understand this correlation, because, you know, when something apparently random here and something apparently random there are strongly correlated, I think it is my duty to understand how it works. Okay. So the first idea is to say, look, we have done a calculation in quantum mechanics. Let us look into the calculation of quantum mechanics and we will find the explanation. And now we have a small problem, which is in fact a big problem, which is the following. If you look at the direct calculation, the one you find in any good book in quantum mechanics, the direct calculation is done in a space which is an abstract space, because it is a tensor product of the space where you describe the first photon by the space in which you describe the second photon. So the calculation is very clear, but how do you make a calculation in our world when you have, how do you make an image in our world when the calculation happens in a very abstract space? This is really annoying, and I like this citation by Asher-Perez. Asher-Perez was a strong Copenhagen theorist, okay? He was not somebody who did not like Copenhagen, etc. But anyway, he was a theorist who said, at the end of the day, the quantum phenomena do not happen in a Hilbert space. They occur in a laboratory. So a laboratory is our real space. And I insist, I want an image in our space. And there is a way to find an image in our space stemming from the formalism of quantum mechanics. We just have to do the calculation a little more complicated than that, but I can tell you that this is standard quantum mechanics, It's co-analogy approved, okay? This way of doing the calculation has been checked carefully by Claude co-analogy, and so it is just standard quantum mechanics, but a little more complicated. So what do we do? Because I insist to describe it in our world, I will suppose that this polarizer is a little closer to the source than the other one, so we first make a measurement here. So I can speak of what happens here. And then we know what happens. 50% chance to get +1 and 50% chance to get -1. So I can get either the result +1 or the result -1. Then what happens? I go to the book of co-analogy or any other preferred book, but it is my preferred book, and you find the famous collapse of the wave function. It tells you after a measurement, you have a new state vector, which is the projection of the initial state vector onto the eigenspace associated to the result of the measurement, which means that I must project this initial state onto the eigenspace corresponding at that. So here, what do I have? I have put this polarizer in orientation A, and I have found +A, which corresponds to a polarization along A. When I project this state vector onto the eigenspace corresponding to that, I get +A. Ah, now this is interesting. This means that just after the measurement, I have a state where the first photon corresponds to this polarization. Of course, it is a result I find. So, yeah. And the second one is polarized same way. But if I find -1, the projection, the famous collapse, tells me that now I have -. So now the second one is polarized like that, and the first one also like that. Okay, can I continue? Yes, of course, because now I can continue the reasoning by saying, now what do I get if I make the second measurement? Well, I just have to read what happens here and what happens there, and it's just a Malus law, and at the end, I find exactly the same result as the one that was written on the previous transparency. But now I have an image in our world, and I'm happy. I am happy, but Einstein was not really happy with this kind of image. Why? Because it seems that when you do the measurement here, instantaneously it changes something on the state of the second photon. And instantaneously, of course, is something which is not acceptable for Einstein. You remember that Einstein developed the theory of special relativity in which nothing can go faster than light. So the idea that when I do something here, it changes instantaneously on the other side is not acceptable for Einstein. So, oops, really, this electric contact is a problem. Wow. Let's do it mechanically. Now, so the measurement on the first photon seems to influence instantaneously at a distance the state of nu2. This is evidently unacceptable for Einstein. Okay. But it's not the end of the story. After all, why do I insist on this image? Strong correlation between events at a distance happen all the time, and we find reasonable explanation for it. For instance, the weather in San Carlos, I am sure, is strongly correlated to the weather in other places in Brazil, okay? Because probably the wind follow in a certain sense, etc. And we are going to make a small experiment to show that really correlation at a distance is not so surprising. Everybody looks at the screen, okay, carefully, and I'm going to ask a question after that. So watch carefully what will happen on the screen when I count 3. 1, 2, 3. What did you see, Vanderlei?
A green spot.
A green spot. What did you see? Green spot. This is unbelievable. They are distant, very distant, and both have seen the same thing. Strong correlation between what they have observed. So we have a very simple explanation for correlation at a distance. It's the fact that initially there is a common information shared by the two photons, so no surprise that when you do the measurement, you find correlated result.
Wait a minute, but it wasn't instantaneous, because the distance between that spot and Vanderlei, the distance between that guy is different. And if opposed to the speed of light, it just looked like it was the
Okay, you want to annoy me, but I know how to reply. The important point is that when E observed the point and E observed the point, they were separated by a space-like interval, which means that there was absolutely no possibility of a signal traveling at a velocity less than the velocity of light from here to there. They were in different light cones, okay? So don't try to confuse them with that. The point, it's still the same thing. So the point is that if you want to explain a correlation between something happening here and something happening there, and these two things are space-like separated, that is, no signal can connect them unless the signal goes faster than light, you have a possibility, you go in the past when the two photons have been emitted, and then each photon brings it in, for instance, both are polarized along the same direction. So no surprise that you are going to have correlation. Okay. So Einstein, by doing this kind of reasoning, came to the conclusion that quantum mechanics is not complete. You have to complete, because in the description of quantum mechanics, all the pairs of photons are described the same way. And Einstein came to the conclusion that some pairs of photons are polarized like that, others are polarized like that, so you need to have a supplementary parameter to describe this difference. But introducing this supplementary parameter was precisely what he had in mind. So he was very happy with this conclusion. But Bohr disagreed. Bohr disagreed because Bohr had the intuition, the strong intuition, that if you complete quantum mechanics, then the consistency of quantum mechanics will fall apart. Bohr had the feeling that quantum mechanics was consistent provided that you accept that it is impossible to complete it. But it was an intuition. All the words that Bohr wrote about that are not convincing at all. I can cite many texts of Bohr. I mean, the only thing which is clear is that he had this strong intuition. Okay. This debate went on between Bohr and Einstein, and to be honest, without much attention from a majority of physicists. Why? First, Bohr and Einstein were all glories, okay? And my friend, all glories, there is a moment when they do not listen to all glories, okay? The young people. That's the way the world goes on, my friend. But there was good reason for young people not to pay attention. Quantum mechanics was accumulating success. It was a time when the young physicists were applying quantum mechanics to understand many wonderful things. Why should they waste time with a discussion about interpretation between Einstein and Bohr? Because you have to realize that at this time, there was no disagreement on the validity of the quantum prediction. Einstein accepted totally the result of the calculation. He just insisted on interpreting differently. So it's a matter of interpretation. Let us use the formalism. These both physicists agree on the formalism. Let us use it. We demonstrate plenty of beautiful things. So young people were doing quantum mechanics without paying attention. The situation changed 30 years later, in 1964, when Bell took seriously the hypothesis of Einstein that you should complete quantum mechanics. So Bell accepted the idea that when the two photons are emitted, they have the same parameter, lambda, a joint parameter. Lambda may be a big complicated object, doesn't matter. The important thing is the same parameter going for the two photons. The result of the measurement here will depend on lambda and the orientation, and the result here will depend on lambda and the orientation. So he defines a function, capital A, of lambda and A, which can take only two values, +1 or -1 at polarizer 1. I insist on that because now you see more and more people who write papers where they write things about Bell's inequality which are just wrong because they forget that to get Bell's inequality you need to have a dichotomic function with +1 and -1, okay? So +1 or -1 here, capital B is a function of lambda and the orientation and can take value +1 and -1. And of course, because all the photons, all the pairs, are emitted with a different value of lambda, you need to describe the distribution of the lambda. And for that, you describe it by a density of probability, rho of lambda, which tells you what is the probability to get a certain lambda, and it is a normal probability, positive and normalized. And with this, you can calculate all the prediction. If you have explicit value for capital R, capital B, and rho, for instance, it's very easy to calculate the coefficient of correlation. It's nothing else than the average value of the product AB. Okay, let us give an example. This example is beautiful. It's the simplest example you would develop if you would spend 10 minutes, 15 minutes thinking of it. The example is the following. We assume that when the two photons are emitted, they have a property which is their polarization. It's just a vector like that. And they have the same polarization, okay? Now, I must find a model for my polarizer. So I want a function with value +1 or -1. A good idea is to say that if the photon arrives along the axis of the polarizer, I get +1. And if it is perpendicular to the axis, I get -1. And I put a frontier at 45 degrees. Could not be more natural. So my function, capital A, I write it like that. It's the sine of cosine of 2 times the angle between lambda and the orientation. And you can check that this is +1 if you are close to the axis and -1 if you are close to perpendicular to the axis. Okay. What do I take for rho of lambda? I know that the prediction of quantum mechanics are rotationally invariant. So I take rho of lambda rotationally invariant. So I take 1/2 pi. Okay? Could not be simpler. With this, when I calculate the coefficient of correlation, I get the red line. Isn't that beautiful? I get almost the same results of quantum mechanics with such a simple model. I get total correlation at 0 degree, total correlation at 90 degree, at 45 degree, 0 correlation, but it's the same for the quantum prediction, and of course, in between, there is a small difference. But it's just to tell you that there is a model that works quite well. But of course, it does not agree perfectly, but the model was so simple, and so you can ask yourself, is there a better model? You go and see your friend who knows everything about Hankel function, Bessel function, who knows? You know, this kind of, Moises knows everything about Bessel function. Okay, so you're asking, Moises, please teach me Bessel function and I will develop a model that will fit everywhere the prediction of quantum mechanics. And so you ask a question, can we do better? And Bell's theorem gives the answer, no, there is no way to do better than what I have shown you. Whatever sophisticated, whatever mathematically sophisticated the model, you cannot do better. How does it work? Whoops, again. It works in the following way. It tells you that you cannot cancel the difference everywhere. What Bell's theorem tells you basically is that you can have agreement between the quantum prediction and such a model as a limited number of points, but not everywhere. So this is a demonstration, or not. This is the result of the demonstration. Bell can demonstrate that if you accept the idea that there are functions capital A, capital B equal plus or minus 1, and a function rho of lambda, definite positive, okay? Nothing more than that, okay? Not the special model, any model of that kind. Then there is a quantity, capital S, which is written here, which cannot be bigger than 2 and which cannot be smaller than -2. And this quantity is the following. It's a combination of 4 correlation coefficients for 2 orientation here, A and A prime, and 2 orientation here, B and B prime. So I'm going to do 4 measurements, AB, AB prime, A prime, B prime, and A prime B. I make this combination with 3 plus sign and 1 minus sign, okay? And with this, I get the result. Bell tells me if you can calculate the correlation with any model with capital A, capital B, and rho, this cannot be bigger than 2. I am not going to do the demonstration now, but if you come and see me at the end, I promise it does not take more than 5 minutes to make the demonstration. It's simple mathematics. Okay. Now, let us come back to the prediction of quantum mechanics, cosine of 2 times the angle. And let us take this specific set of orientation. The angle here is pi over 2, 22.5 degrees. 2 times pi over 8 is pi over 4. Cosine of pi over 4 is 1 over root 2. So you get here 1 over root 2, 1 over root 2, and 1 over root 2. Now A, B prime. If you double the angle, now it's more than pi over 2. So it's minus 1 over root 2. But there is a minus sign here. So it's again 1 over root 2. So the result is that for this set of angle, the prediction of quantum mechanics is that S is equal to 2 times root 2, which is 2.8, etc. Which means that no model in the spirit of Einstein with capital A, capital B, etc., can reproduce this. So now it's no longer a matter of interpretation. Now it's a question that if Einstein is right, you can do this experiment and you are going to find that quantum mechanics is not right in this specific situation. So, this is really annoying. Let me put it here and do it with my hand. That's okay. I will do it. Thank you, but I will do it like that. So now the possibility to complete quantum mechanics, according to Einstein's idea, is no longer a matter of taste, a matter of interpretation. It has turned into an experimental question. Before going further, you find a conflict between something and quantum mechanics. It's a good idea to check what were the hypotheses of your reasoning leading to a conflict with quantum mechanics. Quantum mechanics is so successful. If something disagrees with quantum mechanics, before embarking in the experiment, double check the hypothesis. So what do you need to demonstrate Bell's inequality? That is to say, a conflict with quantum mechanics. First, you must accept that the correlation between what is observed here and what is observed there is due to a common property, lambda, shared by the two photons. And because each photon is bringing this property with itself, and so photon is neutral, okay, itself, I say. And when the photon arrives here, the result of the measurement will only depend on the orientation of the polarizer and on the value of lambda. This is called a local realistic vision of the world. That is to say, you have here a small volume of the space-time, and you make a measurement of something in this volume of space-time, and all the results that you get depend only on parameters which are here. This is why it's called local realism. It cannot depend on something which is far away, not directly, okay? So that's the local realist worldview. And then there is another condition which is less fundamental, which is Bell's locality condition. In order to demonstrate Bell's inequality, you need to assume that the result of the measurement here depends only on the orientation A and not on the orientation of the polarizer which is far away. Bell insisted on this hypothesis in his paper. He said this hypothesis is independent to demonstrate Bell's inequality. Similarly, the distribution rho of lambda, the way in which the lambda are distributed in the pairs, is not allowed to depend on the orientation A and B of the polarizer that will make the measurement later. So this is necessary to demonstrate Bell's inequality. But Bell made an interesting remark at the end of his paper. He said, if you could do an experiment with variable polarizers, that is to say polarizer of which you change the orientation while the photons are propagating between the source and the polarizer. If you could change the orientation, then there is no time for this polarizer to know the orientation of the other one at the moment of the measurement, because if you would know this orientation, it would mean that something is traveling faster than light. So if you could do an experiment where you change the orientation of the two polarizers faster than the time of propagation of the photon between the source and the detector, then you would not need Bell's locality condition, and it would be a pure conflict between the pure Einstein vision, local realist vision of the world, and quantum mechanics. Okay. Let us continue. So now there is a quantitative incompatibility between the local realist view à la Einstein and with quantum mechanics, so an experimental test is possible. Surprising as it is, in 1964, after several decades of big success of quantum mechanics, there was no experimental result available in any journal. Nobody had done an experiment where you could take the result and test Bell's inequality. And this signals something which I think is extremely important. It signals the fact that most of the correlations that we see in the world can be explained by local realist model of the kind of the green spot, and then the thing propagates from here to there, then go to your eyes, etc. Actually, if you think of classical physics, for instance, classical mechanics, you know that in classical mechanics, all the evolution depends on the initial position and velocities. So if you take the initial position and velocity as the value of lambda, you know that all the result of any measurement will depend on that, and it is embedded in Bell's formalism. So any classical correlation that you could describe by classical mechanics will automatically obey Bell's inequalities. Same for classical electromagnetism. You know that the field depends on the currents and the charge in the source. So take the current and the source, current and charge in the source as a value of lambda, and then everything depends on the lambda, and the result will automatically obey Bell's inequality. What is more surprising is that most of the results that you think you have to describe by a quantum mechanical model, anyway, the correlations are not strong enough to violate Bell's inequality. So to violate Bell's inequality, you have really to look into extremely specific situations. So it could have been that people had not noticed this situation, and that by looking into these specific cases, you could find some kind of conflict. So one must find a situation where the test is possible, and this was due to Clauser, Horn, Shimony, and Holt, which in 1969 made a proposal of a practical way of testing Bell's inequality. It was with entangled photon, and there were 3 generations of experiments. After the paper by Clauser, Horn, and Shimony and Holt, 3 years later, there were 2 experiments, one in Berkeley, one in Harvard. I hope you realize Berkeley, Western Coast, Harvard, Eastern Coast, a long opposition between the 2 places. Situation was interesting. In Berkeley, they found quantum mechanics and a violation of Bell's inequality, but in Harvard, they found an agreement with Bell's inequality and disagreement with quantum mechanics. It was interesting. Now, what is even more interesting is that in '76, Ed Fry in Texas, agriculture and mining, or mechanics, or something like that. So, you know, Texas in the middle, and a university devoted to agriculture and mechanics. He did an experiment. It was the first experiment with a laser. Signal-to-noise ratio was better, and he found agreement with quantum mechanics. Anyway, all these experiments were wonderful, but very far, or quite far, from the ideal scheme I have drawn here. This is why, at the same time, in '75, I embarked into a new series of experiments. The goal of these experiments was to be as close as possible to the scheme discussed by the theorists. So I will describe rapidly these 3 experiments, and these experiments were completed in '82, and then in '88, a new generation of experiments started with a new source of entangled photon, and now it's a whole industry. I mean, it is standard nowadays to be able to create pairs of entangled photon, even triplets of entangled photon, etc. So rapidly, let me tell you what we did in our source of entanglement. We used an atom for producing the pairs of entangled photon. It was a calcium atom, and we could excite the calcium atom from the ground state to the excited state with the same parity by using a two-photon transition. You cannot connect directly with a single photon, the ground state to the excited state, to this state, because they have the same parity, but with two photons it works. Of course, the energy has to be exactly chosen, so we added a photon from a fixed wavelength, krypton ion laser, and a tunable dye laser. This is standard nowadays, but in these days it was far from being standard. It was a lot of effort. Okay, we could do it. Then when the atom is here, it cannot decay directly for the same reason. You cannot go from an even level to an even level directly by spontaneous emission. So the atom had no choice. The only thing the atom could do was delivering a first photon, green, and a second photon, violet. And these two photons, if you look at the scheme of the level, you have J equals 0 here, J equals 1 here, so 3 Zeeman sublevel, and J equals 0 here. But if you make the measurement in two opposite directions, you can forget about the M equals 0 level here. There is no probability to emit in the axis, along the z-axis. And so you have to go from here to there, but you have two possibilities, either this path or that path. So you must add the two corresponding states. And these two corresponding states are sigma plus, sigma minus, plus, sigma minus, sigma plus. But sigma plus and sigma minus you can rewrite as a function of linear polarization. And when you do it, and if you don't believe me, look into my book, or look into my home page, and you find that you have exactly the state you are dreaming of, XX plus YY. So the atom has no choice, it has to deliver the pair of photons you want. To give you an idea of, in the first experiment by Clauser in Berkeley, it took him days to obtain accumulating data to obtain a signal-to-noise ratio good enough, okay? Here, in this experiment, with this source, we had 100 coincidences per second. It's not impressive, but you should be impressed for the following reason. In 100 seconds, you get 10 to the 4 coincidence. And the statistical accuracy of 10 to the 4th is root of 10 to the 4th, which means in only less than 2 minutes, you get a 1% accuracy. You know, it makes life completely different because then you can change the parameter and in a couple of hours, you have made plenty of measurements. Keeping an experiment stable for days and days over weeks is extremely difficult. Keeping an experiment stable for a couple of hours is not so difficult. So it was a huge difference. So, I really to buy another one. The first experiment we did was similar to the experiment of Clauser and the other people, but anyway, there was something new. The something new was the fact that we pulled the polarizer far from the source at 6 meters on one side and 6 meters on the other side. Why 6 meters? Because I had a room 13 meters long. Okay, so I mean, that's the way it is. Why did I do that? For the following reason. When you were reading the literature, there were quite often statements like, okay, we know that entanglement does exist. For instance, in the helium atom, the ground state is an entangled state of the two electrons. Okay, we know that it does exist, but it is a property of the microscopic world. When you go at macroscopic scale, entanglement will disappear because it's well known that the macroscopic scale, quantum mechanics cannot work. Okay, so I would ask the question to a theorist, what is the scale at which you go from microscopic where entanglement exists to macroscopic? And then the theorist will scratch his head and say, coherence length of the photon. Good. Lifetime of this level is 5 nanoseconds. Lifetime of 5 nanoseconds corresponds to a coherence length of 1.5 meters. So I pulled my polarizer at 6 meters, and entanglement was there. We found the violation of Bell inequality very clearly at 6 meters. So at least we found that entanglement survives beyond the coherent length of the photon. But it was still the old scheme. Then we did for the first time, a scheme which resembles really what we have seen. That is to say, we could obtain. Again, you are going to laugh. Now you just order from the company, new focus, etc. But at that time, it did not exist. Maybe I can say now it's an old story. I bribed some people in Philips Research Laboratory in Holland, and they produce this for me, you know, after hours, okay? So I got here 2 polarization separator. So it's a cube, and the polarization in this plane is transmitted, and the polarization perpendicular is reflected. Then I put 2 photomultiplier here, same on the other side, and then I have a 4-fold coincidence circuit, and in a single run, I measure plus plus, plus minus, minus plus, and minus minus. Why is this beautiful? For the following reason. In previous experiment, they and we did not have the minus channel. So when you don't have the minus channel, how do? You say, well, it's simple. When the polarizer is on, I have the +1 channel. And if I remove the polarizer, I have the sum of plus and minus. So the difference corresponds to minus. So the idea of this experiment would consist of working with 2 polarizers, then removing one, removing the other one, removing both, and making your cooking with all that. But then you have to maintain everything perfectly stable, and in addition, when you go to the fundamental point of view, you must add some supplementary hypothesis to decide that the test is good. Here, nothing like that. In a single run, you have the 4 rates. And now look, the correlation coefficient as a numerator, which is plus, plus, minus, minus, but it's self-normalized by the sum of these 4 numbers. So you make a run, and you have directly, without any supplementary calibration, the coefficient of correlation. This was gorgeous, and it really worked beautifully. It was a beautiful apparatus also. And the result is here. The quantity S that we measure as a function of the angle starts from 2, goes to 2.7, then goes like that, go to minus 2.7, and goes like that. This curve is very interesting for many reasons. First, the green curve, which is here, is a curve which was calculated before we did the measurement. It's the prediction of quantum mechanics, not in the ideal case, but taking into account the fact that the polarizer were not perfect. Taking into account the fact that when you have it's a complicated calculation, but we know how to do it. When you have some solid angle, then you don't predict 100% correlation, but only 99%, something like that. And you see that all the points come beautifully on the prediction of quantum mechanics. But it also shows you that if you don't look into the specific values of the angles, for instance, if you try here at 45 degrees or 0 degree or something like that, then you find a result which is in agreement with Bell's inequality, and there is no surprise. And in fact, there had been an experiment in the literature. In the 50s, there was an experiment in which people looked into correlation of polarization for gamma photons emitted by disintegration of positronium. But it was a very difficult experiment, so the only thing they had done was doing a measurement at 0 degree, 45 degree, and 90 degree. Bad luck, it's region where you cannot test Bell's inequality. So if you don't have Bell theorem, you don't know that you should focus on this point, you know. Okay, anyway, with this experiment, now we have a serious violation of Bell's inequality by more than 40 standard deviation, okay? 40 standard deviation is beyond any discussion. I remember that the Higgs boson was considered found as soon as they had more than 3 standard deviation, okay? So 40 standard deviation, there is no discussion possible. Okay, now, next experiment. You remember, I told you, are you hungry or, no, it's 55 minutes, that's okay, I can continue. I told you that it would be nice to be able to change the orientation of each polarizer while the photons are in flight. Now, how long does it take? I told you 12 meters between here and there. To travel 12 meters, it takes 40 nanoseconds for light. So you want to change the orientation in a few nanoseconds. It's not easy, huh? Because if I show you here the kind of device, you know, the polarizer is here, here you have a photomultiplier, here you have another photomultiplier, you can rotate it, but hold on. Here you have a multiple shield with lead and various metals. And the reason is that there are some cosmic rays coming. You want to be protected from the cosmic ray because sometimes something happens in the ceiling of your building and there is a shower of particles and you will get a correlation between here and there. So you must protect. So each of these photomultiplying tube is like 15 kilograms. The ensemble is 40 kilograms. You're not going to rotate it in a few nanoseconds, okay? So what did we do? Rather than rotating the polarizer, we built here a kind of, we call it a commutator. It's something which either let light go here or redirect light along this direction. And this one can change every 10 nanoseconds, okay? Now, I put here another polarizer. So this one is in orientation A, this one in orientation A prime. And so the ensemble here is equivalent to a single polarizer going from A to E prime, back to A prime, etc. Same thing on the other side, and now I change the orientation. Now there is a problem. In an ideal experiment, you would like this to be random and this to be random. It was not the case. By construction, our system was periodic. But because we are not totally stupid, the generator driving this one was not the same as the generator driving that one. The frequencies were not the same, and they were drifting differently. So there was no correlation between the periodic stuff. But anyway, it was not really random. It was uncorrelated, but not random. Okay, with this, oh yes, I don't resist the pleasure of showing you how the commutator worked. I ordered the commutator from a company, and the company could not deliver. It's a lesson for young people. And the company could not deliver. The reason why they could not deliver, they knew only how to build small acousto-optic. It is an acousto-optic device. They knew only how to build small one. But I wanted a big one. Why? Oh, it's a classical optics calculation, étendue of the beam, etc. Okay. Well, I wanted a big one. So I said, we are going to build a big one for you. But when they trying to put the transducers on the crystal, because it was too big, there were a difference in the dilation coefficients, and it would break all the time. And so everything was ready. I was despaired. So I began to look into book of acousto-optics phenomena. And I found that water is an excellent medium for acousto-optic effect, especially in the range of frequency where I wanted to work, which is 50 megahertz, okay? So I just put one, so this is water inside, so it's a vessel with water. I put one transducer up, one transducer low, facing each other in the cube, and there was no problem of breaking a crystal. And it worked beautifully. So don't panic. If a company cannot deliver, maybe you are able to build something yourself, okay? Anyway, this is how it works. So it worked. It was anyway a difficult experiment. For various technical reasons, the signal was reduced. So rather than taking the data in a few minutes, we had to accumulate for a few hours. Anyway, it was not weeks, but anyway, a few hours. And with this, we came with a result where we found a violation of Bell's inequality by 6 standard deviations, which was convincing. But for the first time, each measurement was space-like separated from the other one, which is here, because of this rapidly changing orientation. So Einstein causality was enforced. So I told you that a decade later, there were a new generation of experiments starting and still going on. And the big advance is the following. Actually, I knew that this would be a big advance, but I was surprised it took 10 years to be developed. The idea is the following. Rather than having an atom emitting fluorescence photon in all directions of space, they used a nonlinear effect called parametric down conversion. You heard of it already, in which you have an ultraviolet photon that gives, let's say, 2 red photons. But because there is a Probably some of you have already seen that, a so-called phase matching condition. The two photons are going to meet it not randomly in space, but in well-defined direction. And if you emit your entangled photon in well-defined direction, it's wonderful because then you can inject them into optical fibers. And once you have them in optical fiber, you can make the measurement at hundreds of meters. In this experiment in Geneva, Nicolas Gisin makes measurement at tens of kilometers. He uses a commercial network of Swiss Telecom to do his measurement. At night, Swiss people sleep. And meanwhile, Nicolas Gisin is doing experiments on the commercial network of Swiss Telecom, okay? There was also this beautiful experiment done in '98 in Innsbruck by Zeilinger and Greg Weiss, in which, again, inserting the photon into optical fiber, they could do the experiment I was dreaming of, but I could not do 15 years earlier, in which it is while the photon is traveling, then there is a random number generator that decides on the orientation of the polarizer. This random number generator is fast enough that it can be done while the photon is propagating. So now it's really random. Okay. And then they detect the results, there is an atomic clock, there is another atomic clock, and only when everything is finished, they compare the result and look for the correlation. Okay. Agreement with quantum mechanics. This was the first repetition of our third experiment, and I must say I was relieved when I say, because you never know, you can always have a problem in your experiment. They found the same result as us, agreement with quantum mechanics. So what can we say? We can say that there are more and more sophisticated check of Bell's inequality and all the experiments. I don't want to discuss too much loopholes and things like that, but there is more and more evidence that Bell's inequality are violated whatever you do, provided that you do your job well. Okay. So we have to accept that Bell's inequality are violated and that Einstein's local realism is untenable. What can we conclude? Well, Einstein himself told us. So I suppose you are going to be surprised. Einstein was considering the possibilities that he was wrong. Yes, he was using it as a reasoning ad absurdum. Einstein would tell us, if I was not right that we must complete quantum mechanics, this is what you would have to face. And these are the words of Einstein. If quantum mechanics could not be completed, one would have to either drop the need of the independence of the physical reality present in different parts of space. When he says space, he means space-time, okay? Space-like separated. Or accept that the measurement on one system changes instantaneously, Einstein word, instantaneously, the real situation of S2. Of course, Einstein could not accept that, so he concludes that you have to complete quantum mechanics. But we know that we have to accept one of these two things. Actually, personally, I think that these two things are more or less equivalent, because this one means that what you have here is not independent of what you have there, and when I say here and there, I mean volume of space-time which are space-like separated. No possible connection by a signal unless the signal goes faster than light. So the first thing say independence of here and there, and the second one say when I do something here, it changes instantaneously what happened there. For me, it's about the same thing. We have to accept something of that kind. This is called quantum non-locality. Other people prefer, and I don't choose, well, my choice is more quantum non-locality, but I think this is also a very nice point of view. Other people prefer to speak of quantum holism. What does it mean? It means that the violation of Bell's inequality tells us that when I have my pair of photons, they are far from each other, but I am not allowed to consider them as, I am not allowed to consider the system of the two photons as the sum of the properties of this photon and of that photon. There is more in the pair than in the sum of the properties of what you have here and what you have there. And this remark is fundamental because I think that it is a fundamental remark at the root of quantum computation, as I will show in a moment. The fact that there is more in the pair than in the individual component is the reason why there is the possibility to store a fantastic amount of information in entangled system. Not that there is no possibility to use quantum non-locality to transmit a useful signal faster than light. By useful signal, some people would say I push on a button here and the bomb explodes elsewhere. It's not a very nice thing, but it would be faster than light. Other people say, oh, I could give an order for the stock exchange in New York and it would arrive faster than light, okay? Some people are excited by that because, you know, fast trading and things like that. It's not possible, okay? You cannot use quantum non-locality for transmitting a useful signal faster than light. If you ask me the question, I will explain you why. But maybe you will be angry. So a few words about the new quantum revolution. By the way, books. This one I already told you. You asked to have it in your library. This one, John Bell. The papers of John Bell of the Foundation of Quantum Mechanics. Wonderful paper, full of humor, okay? The title is Speakable and Unspeakable in Quantum Mechanics. It's published with Cambridge University Press, and there is a foreword of Alain Aspect saying why he thinks that this is interesting. Okay. This book by Nicolas Gisin of Geneva, Quantum Chance, it's a kind of popular explanation of all these things. I like it very much. The idea beyond this book is that Nicolas Gisin in Geneva, the idea is that what makes impossible to transmit information faster than light is the fact that there is a fundamental randomness in the quantum measurement. When the photon arrives here, you don't know if you are going to get +1 or -1. Okay? And this fundamental randomness is what, if you could force this, then you could transmit information faster than light. I think it's an interesting book. New quantum revolution. Understanding these extraordinary properties of entanglement has triggered a new research field, quantum information. A few dates. Richard Feynman, I already cited his paper. It's very interesting because in '62, in Lectures on Physics, you all know, I hope, the book Lectures on Physics of Feynman. He wrote, the only mystery of quantum mechanics is wave-particle duality for a single particle. And he explicitly cited the Einstein-Podolsky-Rosen paradox and said, there is nothing interesting in that. 20 years later, he comes with his paper and says, I made a mistake, I'm sorry. It is very interesting. Entanglement is really something completely different. And again, Feynman being Feynman, then he says, let us use it, and he invents the idea of quantum computing, 82. Then there is David Deutsch, 85. Quantum cryptography, Bennett and Brassa, 84. But this paper was unknown until Arthur Eckert in 91 found another method of quantum cryptography. It's based on entanglement. Quantum teleportation, based on entanglement. Quantum simulation, based on entanglement. So entanglement is at the root of most of the schemes for quantum information. And I just give you a flavor, because after this talk is well adapted, of what is Arthur Eckert's scheme for quantum cryptography. You know what is cryptography, okay? You use it all the time when you send your number of credit card on internet. You hope that there is a safe process. It's called the RSA algorithm for keeping it from the eavesdropper. Okay, the eavesdropper is the guy who is trying to spy. So, at the end of the day, quantum cryptography can be reduced to the following problem. If Alice and Bob, the two friends, have two identical copies of a random series of 1 and 0, Alice can use this to encode, and Bob can use a copy for decode, and this is absolutely sure under the following condition. They are allowed to use this encoding and decoding key only once. Because if they use it more than once, then the eavesdropper will notice some repetition, some character comes more often than other ones. That's the standard way for deciphering the codes, okay? So the problem is the following. They have exchanged a message, and now they need to renew the key. How do you renew the key? Well, entangle photons. Entangle photons. If you have now here a source of entangled photons, and you send one photon here and one photon there, and they have when they have the polarizer along the same direction, then it's randomly plus plus or minus minus, and they have an identical copy. So the scheme is the following. They have decided in advance that they would go from one only a limited number of orientation, okay? So they do the experiment, they register everything. When it is finished, they communicate by open radio. Everybody can spy, okay? And they say, for the first measurement, my orientation was this one. The second one, my orientation was that one. And they know which measurement corresponds to parallel polarizer. And this will allow them to have the key. Okay. Now, you are going to tell me, but the guy who is here may be smart. He may introduce a detection here, look at what he gets, then he sends the same photon with the same polarization as the one he found. If he does that, now it's no longer an entangled state, because as soon as he has made the measurement, the photon has a given polarization. So from time to time, Alice and Bob decide to take a subsample of their data and to test Bell's inequality. If there is a guy making a measurement and resending a photon, Bell's inequality are not going to be violated, because then there is a real value for lambda. So this is the idea of the scheme of Arthur Eckert. Okay? This is one of the schemes of quantum cryptography, but you understand what is the interest of quantum cryptography. In traditional cryptography, you make the assumption that your adversary, your enemy, is not much better than you in technology and not much better than you in mathematics. For instance, the famous RSA algorithm is based on the fact that it is very difficult to factorize big numbers. But there is no proof that there is not a theorem of mathematics allowing to factorize big numbers. Let's suppose that your enemy has the theorem. Your system is not safe. With quantum cryptography, the security is based on the fact that the quantum laws are valid. So you can tell me maybe someday they are not going to be valid, but we think that it is solid laws, okay? So the difference between classical cryptography and quantum cryptography is that in quantum cryptography, the reason for security is only the validity of the quantum laws, while in classical cryptography, you must make the hypothesis that your adversary has not computers 1 million times faster than yours. Because if he has a computer 1 million times faster than yours, he will be able to factorize big numbers. Or if he has a good mathematician with a good theorem. Okay, so this is an example. We heard about quantum computing, so this is the nice apparatus of Rainer Blatt. Rainer, see, I always cite your system, okay? It's not because you are here. It's my preferred image. Thank you for providing it. Okay, so quantum computing, you heard about it. Let me again, anyway, repeat that, as Rainer told us yesterday, the real basis of quantum computing is massive parallelism. Why? Because again, as I told you, in a system of entangled particles, there is much more information than in the classical addition of the properties of the various systems. And just to give you an idea, this is what he cited yesterday. You have 2 qubits. What is the size of the space? It's simple. You can have plus plus, plus minus, minus plus, minus minus. Dimension 4. 3 qubits, dimension 2 to the third, 8. 10 qubits, dimension 2 to the 10, which is 1,000. 20 entangled qubits, dimension 1 million, etc. So let's suppose we have 20 entangled qubits. He could have 20 entangled qubits, but he told you there are other problems. Then the size of the Hilbert space is 1 million, which means that in a single operation, you make 1 million operations. So the idea of quantum computing, which is massive parallelism, is based on the fact that when you have an entangled system, there is much more information than the sum of the information of any individual system. Okay. We don't know if we will have a quantum computer one day, but we have one? Okay, we have one. And maybe we will have one on the desk one day. There is something slightly different, which already works. We heard of it also. It's quantum simulation. That was the initial idea of Feynman. I don't want to elaborate much, but for instance, in my lab, we simulate the motion of electrons in disorder materials, not in perfect crystal, but in disorder material. And for instance, we have observed this is a photo of a wave function of particles which are Anderson localized, for people who know what it is. I was very pleased when we observed that. And so I think that really we have a new quantum era, maybe a new quantum revolution. And I would like to draw your attention on the fact that not only we need for this new revolution entanglement, I have insisted entanglement is different, entanglement is not wave-particle duality, it demands several particles, etc. But there is another thing which made fantastic progress during our active life, right now. When we started to work in physics, nobody was thinking that it was possible to observe, control a single quantum object. And it is during our scientific life that we have seen people like Demelt, and then people like him being able to trap single ions and observe quantum jumps. People develop atomic force microscope, allowing to see individual atoms and to manipulate them. In the experiment I have described, I was able to produce pairs of photons that you can identify individually. If I was doing a correlation between one photon of one pair and one photon of another pair, I would not have a violation of Bell's inequality. So it was individual pairs of photons, etc. So I think that the new quantum revolution is due to two factors. First, understanding that entanglement is very important, and second, this ability to control, observe, and manipulate single quantum objects like ions or photons or things like that. With this, you can ask a question, why do I speak of a revolution? Well, the first quantum revolution, based on wave-particle duality, not only allowed us to allow them, our fathers and grandfathers, to understand the structure of matter, its properties, its interaction with light, understanding exotic properties like superfluidity, supraconductivity, etc. But these inventions, laser, transistor, integrated circuits, which are at the root of the information and communication society, right? This is based on the first quantum revolution. So it was not only a conceptual revolution, but also a technological revolution. So now, will the new conceptual revolution, entanglement plus individual quantum system, give birth to a new technical revolution? Rainer thinks yes. I don't know, but he's younger than me, so not much, but slightly younger than me. So he thinks yes, I don't know. So the most likely roadmap is from proofs of principle with well-defined elementary microscopic objects to solid-state device. It's a fascinating issue. We live exciting times. And to conclude, you have seen what are the heroes, the visionary fathers of the quantum revolution: Einstein, Schrödinger, who realized also as early as 1935 that entanglement is definitely different. Bohr, who had the intuition that interpreting entanglement according to the classical Einstein view was incompatible with quantum mechanics. Bell, who found the proof of Bohr's intuition, and Feynman, who realized that entanglement could be used for something. So we stand on shoulders of giants, but we also stand on the shoulders of our collaborators. In the 82 team, there was Jean Dalibard. At that time, he was younger than that, Philippe Grangier also, and two wonderful engineers. And nowadays, there is this group of atom optics people who work on quantum simulation with cold atoms, and postdoc and PhD are welcome. And with this, I thank you very much for your attention.
Thank you very much. much, Alain. Before we start the discussion, I would like to make an announcement. We would like to take a picture of all of you here in front of the stage. So don't run away. Nós vamos fazer uma foto depois da discussão, tá bom? So it's,
questions?
Questions.
Yes. I saw that he was not sleeping. Okay, he was following.
So,
monsieur. You have been scooped. I'm sorry.
So EPR, all we can do is humble accept the result, right? But there's another thing which I even find more mind-boggling. You take a photon and you make it interact with 10 to the 23 particles, and then you get a collapse in Hilbert space to an eigenstate. I find this even more miraculous.
Well, there are many things which are weird in quantum mechanics, but the way you present things is not precise enough. We should really describe exactly what you have in mind, and then we could talk of it. My first reaction to what you say is that if you have only a single photon, I think we still are in the framework of single particles, and for me, this is still the first quantum revolution. And I may elaborate a little bit, sorry to be a little too technical, why I think that it is radically different. When I think of wave-particle duality, it means that the same object, let's say a single photon, or a single electron, or a single neutron, from a certain point of view, I can describe it as a particle with a trajectory, and when going on a beam splitter goes either on one side or on the other side. But from another point of view, I have to accept that it behaves like a wave, which is spread in space, and going on the beam splitter, a part will be transmitted, a part will be reflected. And you can notice that I have used concepts which are all living, which are all evolving in the ordinary space. I say a trajectory, it is in our ordinary space-time. I say a wave, it is in our ordinary space-time, 3 coordinates plus time. I think that, yes, it's weird that the same object can be both a wave and a particle, but anyway, the words wave and particle are still classical concepts that we can develop in ordinary space-time. Entanglement is another story. There is no way to describe entanglement in the ordinary space-time. You have to describe it in a Hilbert space, which is a tensor product. And if you insist, this is what I did, if you insist on describing in the real space-time where we live, then immediately you have to face non-locality. I tend to think that what you signal is more on the first kind, but I don't disagree that it is weird, but I tend to think that it belongs to the first world.
But I was really asking about the reduction of the wave.
Yes. Yes, but I could tell you that there is a hidden variable model, the model of Bohm, who, by the way, taught in Brazil long ago, and the hidden variable model of Bohm for a single particle works. It's complicated, it's not very pleasant, but if you insist, you can have this model of Bohm, which is classical-like. But if you try to use a Bohm model with entanglement, then again you have to face non-locality. The Bohm's model becomes non-local, that is to say it violates relativity if you want to use it for two particles. When you have a single particle, you can still, if you insist, use classical images. But I agree with you that it is weird. I don't disagree. I just say that there are two levels.
So I have two questions. The first one is actually, you said that the quantum mechanics have 2 points of view, the interpretation and the mathematics point of view, that you only see actually the functions. Do you think that choosing one of these points of view can actually change the facts which you are analyzing, the ideas that you are about to have, the theories you are about to create? Do you think there is some kind of interference based on your point of view on these quantum questions?
Okay. So this is the first question, okay? I answer this one. It's a difficult question. Can discussion on interpretation change something? Well, first, I don't know, maybe. But at least I know some things that this has changed. The people who accepted to look into the fact that it is really weird, really unbelievable, these are the same people who have invented the basic concepts of quantum information. So accepting to discuss interpretation, which does not mean you don't say it is wrong. You say it's unbelievable. How could I interpret that? And you realize that it's really the point of view of Feynman. Because it's so surprising, there should be a way to use it. So at least it changes that. So I think, at least from this point of view, it's very interesting. And maybe we will find, maybe there will be a real progress in, I don't know, because as a scientist, we cannot think that quantum mechanics will be there as it is forever. We all believe that one day or another, there will be a bigger theory incorporating quantum mechanics as a limiting case of I don't know what, okay? And maybe that this kind of discussion will lead to the discovery of that. I don't know. But even if we don't have that, at least, again, you are young. If you find something that you find extraordinary, don't listen to people who say, okay, but you know, the equations are good, so don't take. No, think of it. Maybe you will invent something. Second question.
The second question, I think, is a bit harsher. I studied superficially the concept of tachyons and
of what?
Tachyons. The tachyons.
Tachyons.
Tachyons, yes. So, as you said, theoretically, in the world that we live in, there is no speed above the light speed.
I don't think it is the same kind of thing. Because in tachyon, people think that there is really something like a particle traveling faster than light. Here is something else. Here, it is a fact that if you insist on describing it with images, that you have to borrow from our usual experience, wave, particle propagating in our ordinary space, then you have to admit something like a non-locality. But this is what you have to face with, for instance, the first quantum revolution. The collapse by itself is instantaneous. But what I know is that these images, crazy as they are, never lead you to predict a useful something real traveling faster than light. It's just in your image. I think that the tachyon is different. I think that the people, first I am not an expert, but I think that the people who develop the idea of a tachyon think of a real, that there is a particle going faster than light. It's not the case here.
Yeah, the actual question was to ask you if all these problems around the tachyon theory, if there is an piece and space for the tachyons along the quantum mechanics, or just another
Honestly,
theory?
I don't know. You have to ask to sophisticated theorists, okay? I'm not one. I think I understand a little bit of quantum mechanics, but I am not one of the theorists.
Very much.
Okay. Other questions? Robin has a question. Oh, I've known him for decades and he still has questions. He's wonderful. Vanderlei, same. I've known him for decades and he still has questions. But Robin first.
So I have a question. When you mentioned the value inequalities,
The what?
value inequalities, you stress and appreciate that one of the assumptions, if you have a theory, there's always assumptions. And one of the assumptions is that the outcome of the result is binary.
Yes.
So here we discussed at some point. Do you know if there's a theory which could prove or lead to an quantum proof of entanglement if you don't have a discrete outcome?
Yes, but it's never as strong as Bell's inequalities. I mean, it's all this entanglement witness, and you know, it's a. But I mean, violating Bell's inequality is so clear. There is no discussion possible. Okay. But in order to have valid Bell's inequality, you must be in a situation where you have a dichotomic observable. Okay. But you are right. There are plenty of other witnesses of entanglement. Well, there are several kinds of inequalities, that Mermin and things like that. Yes, but all this becomes technical. But I think it's interesting, but it's really technical. I don't think so. I mean, in principle, you can have violations with an as large number of particles as you want, but it's more and more difficult to make it, like the Schrödinger cat. In principle, nothing prevents the Schrödinger cat to be realized, but in fact, I mean, it's more and more difficult. So I think that you have to face the same problem. Entanglement of more and more particles is more and more difficult to preserve and to have a strong entanglement. Yes, Vanderlei. Professor Vanderlei.
Yeah, the question is, you know, you being involved with these interpretations and fundaments of quantum mechanics using the photons and everything. If you have to give us an idea, what are the new challenges in that direction, what would you say? I mean, suppose I'm going to start to think about what you think will be a good experiment or a good spot to think about in this area of fundaments of quantum mechanics.
What he is doing, working on the quantum computer, either the quantum computer with logic quantum gates or quantum simulation. He quoted it, this is my choice. This is what we do in our lab. We try to play with the quantum simulators. That is to say, the many-body problem, that is to say, entanglement of many particles, and trying to progress, because this is a domain where there are many, many things to discover. And depending on your spirit, if you are fundamental-oriented, is interested, but I'm deeply convinced that even if you are engineer-oriented, this is called quantum technology. And there will be places where these concepts will be useful. The simplest one looks ridiculous, but it's very efficient. It's a random number generator based on the fact when a photon arrives on a beam splitter, there is absolutely no way to know if it goes on one side or on the other side. And there are some random number generators based on that. They are fundamentally better than any computer generation of a random number. So it's an example. I think that there are places where the quantum technology will play a role. So I think going towards either logic gates or quantum simulation, but having several entangled objects is a very fascinating subject, I think. But there are many other subjects in the
Me.
Paolo.
Maybe one comment just on what you just said and something you put in your presentation, which I think is very nice. Freeman Dyson mentioned the origins of scientific revolutions, and he separates them in concept-driven revolutions and technology-driven revolutions. And you're basically showing us a picture in which both are playing a role at the same time. So just
Yes.
to make a connection with what you
It's
just
an
said.
interesting comment, but for instance, I happen to have read interesting books about the invention of transistors. You cannot know if it is concept-driven or technology-driven, because the people in the United States realized in the late 30s that the computer with tubes was a dead end. And they had to find the equivalent of the triode or the pentode in solid state. And it was a coordinated effort in all American universities and national labs to find a way to replace the electronic tubes with what had to be the transistor, okay? And this was discovered by the most sophisticated theorists, okay? But initially, it was really prompted by an application, by a demand for application. So in this case, I think you cannot disentangle the two things, but your comment is very interesting. But I think, well, my lesson to young people is do whatever you like. If you like applications, think application. If you like basic principle, think of basic principle. But if you think of basic principle, if there is a possibility of application, think of it. Do not miss it.
So the second part is based on the comments on the collapse of the wave function.
Yes.
There's little discussion, I find, about Bell's inequalities in relativistic settings, meaning that, for instance, one detector is moving with respect to the other, and you're forced to have more than one reference frame.
Yes.
Could you make a comment on that
Yes.
and how,
Yes,
how
I can.
Bell's inequalities
I can very
Lorentz
easily.
invariant?
I can very easily. First, when people tell you that what we do is not relativistic, it's wrong. Quantum optics is relativistic by construction. And for instance, if you go to my PhD thesis, which is on the web, but you read French, no problem. I do a full calculation where everything is taken into account, retardation times and things like that, and there is no doubt that the formula that we write are written in the relativistic formalism, because by construction, quantum optics is a relativistic theory. Now there is these experiments of Nicolas Gisin where he moves one detector. Yes, it is a fact that as soon as you have something which has an apparent non-locality, which means that two events which are space-like separated seem to act upon each other. Of course, we have all the usual paradox. That is to say, the fact that if I change a frame of reference, one will appear to be before the other one, but still space-like separated, or it will be the reverse, but still space-like separated. So you are right, but I think it just adds to the paradox. But having two events, space-like separated, and seemingly having an influence on each other, is not more surprising to have it at the same time, but space-like separated, as with reverse time like that. So I think that we are in the same degree of mystery. The important point is space-like separated. Once it is space-like separated, you can change frame of reference. It's always space-like separated.
My question is kind of a general one. It's really addressed to you and to Rainer at the same time. And it has to do with the future, this question of the future of quantum computation and
quantum technologies in general?
Quantum technology, the idea of, yes, that we're going to have a quantum world in a way which goes way beyond very fundamental experiments in physics. And my question is really the following. There's been developments using photons have been tremendously impressive, to the point where now quantum cryptography is actually a commercialized technology.
Yes.
And the reason for that, the reason it seems to have bounded ahead is because the trouble with, the difficulty with coherence or decoherence is much reduced in the case of photons than it is in the case of massive particles, either ions or atoms, etc. So my question is, what is the future? Is there, decoherence has been a tremendous problem for those